All right, let's do these graphing problems. So, on part A, we have two things happening to the graph of cosine. First, we've got a horizontal shrink. Remember, whatever happens to the x happens the opposite. Then we've got a -1 on the outside. That's going to happen to the y values, so it's a downward shift. Okay, so we're going to start just by graphing normal apparent function cosine of x. So cosine of 0 is 1, cosine of 90 is 0. Draw yourself a unit circle if you don't remember these. And so the 1s and 0s are 90 degrees apart, and we're going to make a wave pattern. So 1, 0, -1, 0, 1, like that. So there's our wave pattern. And then in the negative direction as well. So go over 90 degrees, there's the next one, over 90, over 90, over 90, like so. And connect the dots. Okay, so that's just regular cosine of x. So we want to do two things. We want to shift it down 1. So that means our center line is going to be at -1. So I'm just going to sketch that in. And I missed. You don't have to watch me erase. Hey, look at that beautiful center line I drew. So, y equals 1. That means that cosine is going to be going above and below this center line right here. So it would have a maximum of 0 and a minimum of -2. Okay, now it's also going to get shrunk horizontally. So instead of the important points being a distance of pi over 2 away, or 90 degrees, like they were when we graphed the original sign, how far are they going to be? Well, shrink that distance by 2, they're going to be 45 degrees away. So I'm going to start, shift it down 1 to 0. That's still the top of my wave. And now the middle of my wave is going to come, again, not 90 degrees, but 45 degrees away. So at 45 degrees. So then there's the middle of the wave, which is at -1. And then the bottom, and then the middle. So again, counting over every 45 degrees because of our horizontal shrink. And then the top of the wave, the middle, the bottom, the middle, the top. So again, the top is going to be at 0, the bottom is going to be at -2. And we go in the negative direction again, counting over 45 degrees. There's the next point over 45, the next point over 45, the next point, next point, next point. And our wave looks like this. So shifted down 1, so it's centered around y equals 1, and horizontally shrunk by 2, so that you see twice as many waves in your picture. And all the points are twice as close together on the x-axis. Now, let's try the next one. So the next one is a sine function. So we're going to start by graphing sine. So sine starts at 0 and then goes up to 1. And again, for the normal function, these points are spaced out every pi over 2, like so. Easy way to remember that, those are the angles that are on the axes. So sine, cosine, they're always 1 or 0 or -1. Okay, so there's sine, that's what we're going to start with. We've got two things happening. We have a horizontal stretch. So our wave's going to get stretched out. And we have a horizontal shift. Now, this phase shift is important. That's going to give us our place to start our wave. So sine, usually we start at 0 and then wave from there. Here, we're going to use the value for our phase shift and wave from there. So the phase shift, write in pen, is -c, that would be pi over 4, divided by b, which would be 1/2. So -c, which would be pi over 4, And instead of writing it as divided by 1/2, we're going to take that fraction, flip it, and multiply. So times 2 over 1, which reduces to pi over 2. So that's our phase shift. So we're going to start our graph from pi over 2 instead of from 0. So the phase shift shifts this 0 point over. It's going to be right there. And it's not moving up or down, so it's going to stay as 0 on the y-axis. So again, the phase shift shifts our starting point of our wave over in one direction. Here it's going to be to the right by pi over 2. And now we need to wave. So sine starts up, but how far does it go over? And so remember, for sine, these points are spaced out every pi over 2, or 90 degrees. Here, we're doubling the x values. So if we double that, we're going to get pi. So that's how far apart our important points are going to be. So instead of counting over pi over 2 to put the next dot, we're going to count over a full pi, twice as far to put the next dot, which would be up there. And then we would go over twice as far for the next dot, which would be over there. So something like this. And then in the negative direction, again, we count over pi to put the next dot, count over pi again, and then over pi again if we had more space. So down like that, and up, and off in that direction. So there's our graph. It's stretched out. So calculate the phase shift, and then use this value for b to figure out how far apart your important points are. Now, let's do this last one. Again, this is based off of sine. Since it doesn't give any indication of whether you should use degrees or radians, it doesn't matter. So I did this in degrees. And so I'm going to graph sine, again, going over 90 degrees for the next important point. So sine of 90 is 0, sine of 180, like so. And then in the negative direction, sine of negative 90 is negative 1, then 0, then 1, then 0. Make a wave. Okay. So this negative on the outside, what does it do? Well, multiplying by a negative always gives you a reflection. If that reflection is on the outside of the function, it's going to affect the y value. So it's a y reflection. So in other words, all the y's are going to switch sides. So it's across the x-axis. Even though it's affecting y values, you flip across the x-axis. So a little confusing there, but it's what happens. And so instead of starting up, this point at 1 is going to be at negative 1, and we're going to start down like that. So the points at 0 when you reflect aren't going to change, but the points at 1 or negative 1 and all the points in between are going to get reflected. So we get something like this. Okay, so there's the graph. And the instructions ask for another function that would have the identical graph. So we talked about a couple of them on the last quiz. One would be y equals. So instead of flipping it vertically, we could also flip it horizontally to produce that same graph. That would be sine of negative x. Another one would be sine of x plus 180, because it shifted to the left, 180. That would be another way to get the same graph. Another way could be, to get this red graph, could be cosine shifted to the left, 90. Y equals cosine of x plus 90. Things like that. If you can do sine of x plus 180, then add another 360 to that, get a coterminal angle. You could do sine of x plus 540, etc., etc. Okay? Now, I'll briefly discuss this last one, number 7. I'm not going to write out an entire answer for you. But remember, the word periodic means repeating. And so a lot of different behaviors repeat. So the obvious example here, since we talk about waves, would be like, hey, waving. So pick another example. We talked about several in class when we first started talking about these different waves. And so try and explain why a trig function, which also repeats, it makes a good model for some sort of periodic behavior. So what is it about trig functions that makes them good to describe these types of behavior? And you can use examples in your explanation as well. So try that. We'll talk about it. I want to hear what you have to say about it on the test. So that's going to be it. Come to class prepared. Have questions, and I'll leave plenty of time to answer them. If you don't have questions, then I'll assume you're ready for the test, and we'll just go ahead and start. So I'll see you then.